Alright guys, welcome to day 2 of experiments in observational studies, or what I'd like to call how to experiment badly. It's weird. Sometimes when you're trying to understand something, it's a lot easier to say what not to do than all the wonderful things that you can do. Experiments are wonderful things. They really do lead us to a lot of discoveries and a lot of conclusions, and they point out a lot of cause and effects relationships. However, I think all of us have seen when experiments go bad. And so that's what we're going to look at today. What can we do to make sure that this doesn't happen, or how can we recognize it when it does? Now again, we like to do experiments because it allows us to examine a cause and effect relationship between one variable, an explanatory variable, and another, the response variable. We do this because we are controlling our outside influences. We're specifically saying, okay, the only changes between these two groups are going to be A and B. And because of that, we can monitor that cause and effects. We can pin down exactly where that cause and effect relationship occurs. Now, in order to have this happen, we have to have a good design. It's not just something that randomly occurs. There are things that we have to take into consideration. Here's an example. A high school regularly offers a review course to prepare students for the SAT. It says this year, budget cuts will allow the school to offer only an online version of the course. Over the past 10 years, the average SAT score was 1620. Now this is obviously over the 3 different sections. The online group gets an average score of 1780. Now that's a roughly 10% higher than the long-time average for those who took the classroom course. Is this review course more effective? Now, to somebody who's just looking at it, they're going, of course! Rather than getting 1620, we have 1780. Oh my gosh, that's huge! I want to take that online course. But is it really as good as all that sounds? What this is this is a very common approach towards experiments. And it's a very simple approach. An experimental unit is chosen, a treatment is applied, and then we measure those responses. Nothing's wrong with that, right? That sounds completely perfect. And you know what? In a lot of cases it is. That's a great approach to take. But the problem is life's not always that simple. This is what we can do in labs. If you're in chemistry and you want to measure the effect of one acid on a substance, yeah, you identify your units, what are your substances, the treatment is the acid, and you measure the response. But field experiments, real world life, that's not that simple. There's other things going on, and we have to take those other things into consideration. So outside the lab, badly designed experiments yield worthless results because of confounding. Can we go back to this example up here? Is it really that simple? Is it really just the online course that affects the outcomes? How many students took the course to begin with? How many students were in the online course? You know, if there were only 4 kids in the online course and they were all the best students, yeah, you're going to see a difference. You have to know more about what's going on. You can't just blindly accept these things. There are other aspects, other variables, lurking variables, confounding variables that affect what's going on here. Okay, so when we're looking at these confounding variables, we say that when one level associates with another level, those are confounded. Because we cannot separate the effects of one factor from the effects of another. So if we're trying to do multiple things to something, for example, measure the success of students in statistics, but I change and do a flipped classroom and I change the tests, I don't know. Is that because of the way I taught the lesson, or were the tests easier? So that linkage has been confounded. Confounding arises when there are other values, other variables associated with a factor that has an effect on the response variable. Other things that affect the factors. Now, an experimenter assigns treatments, hopefully at random, to subjects rather than just observing them. A confounding variable cannot be thought as a cause and effect for that assignment, because you're controlling these things and you're hoping that through random assignment, what might be a lurking variable in one case is balanced out over several different cases, because we're controlling my treatments. A confounding variable can be associated in a non-causal way with a factor and still affect the response. Because of confounding, we find that we can't tell whether any effect we see was caused by our factor or the confounding factor, or if it was both working together. So if I change your tests more than just numbers or the order of the words or the difficulty level of it, I can't tell, was it the fact that you guys got a little bit more practice in class that helped? I really can't tell. Okay, so this is basically just a little bit more of a review of what we talked about last time. So when we want to experiment well, we have to do a randomized comparative experiment. And that title pretty much says it all. Randomized. We truly hope that our variables, our factors, are assigned randomly. Comparative, we want to be able to compare the results from those different factors, from those different treatments. An experiment, we are controlling it at every stage to try to measure and create a cause and effect relationship. And so what happens is some units will receive one treatment, and then similar units will receive another. So we are using the term units because we're not limiting it to just people here. It can be anything that we're talking about. But the big thing is that we are comparing similar units. Comparison alone isn't enough, because if your groups vary greatly, we will have bias. Remember, bias is anything that skews the results towards one group or another. And again, to control that bias is random assignment, hence randomized comparative experiment. So in an experiment, random assignment means the units are assigned to the treatments at random using some sort of chance process. Now, a lot of times we'll go back through and we'll use our SRS, our simple random sample, to assign treatments at random. We'll have some sort of a list from which we can assign treatments. Other times it'll just be a pull from a hat type of experiment. But you'll have to make sure that you see somewhere in there that the treatments were assigned randomly. Must be actually stated somewhere in what we're doing. Now, a completely randomized design, the treatments are assigned to your experimental units completely by chance. So that assignment is completely random. Sometimes we'll include a control group that receives an inactive treatment or existing baseline treatment. Those of you who are taking AP Psych, y'all have seen this before. You might know this as placebos. So here we've got an example of a completely randomized design. And I want to point out a couple of things that you must do. This is a visual way to represent a treatment design, an experiment. Whenever you do an experimental design, a design is always a descriptive technique to explain what's going on, and typically we'll use a picture to do this. You must start by identifying your experimental units. Now that means telling me who we're talking about, and if those units have labels, do so. If they are 30 AP statistics students from the Battlefield High School statistics classes. Okay, those are my experimental units. Then we have random assignment. Now, I want to make sure you guys understand something. This isn't just put here for giggles. You must always include this. You must state that whatever was done through random assignment. You don't necessarily have to go through and tell me what that random assignment process was, but you have to physically come out and say that your groups were assigned randomly. Maybe our groups are groups based off of block periods. Maybe our groups are based off of teachers. The groups themselves we've broken them down into Group A and Group B. So maybe we're talking about students who have AP Statistics 4th period versus students who have AP Statistics 5th period. Now those groups themselves are not the treatments. Those could be something simple as Group A and Group B, Group 1 and Group 2. But we have to then state what the treatment was that we apply to those groups. Sometimes within each group we'll have even different treatments. But maybe the treatment is that the block 4 students have Mr. Metz and the block 5 students have Miss Augsburger. You see, it's not the groups themselves here that we're talking about. This is the treatment. And then what we're going to do is you always must put this at the end. Again, this is extremely crucial. You must use these words. You must state, compare results. Otherwise, why are you doing this? Your goal from an experiment is to compare your results to see what the difference is. You must compare your results, and you must state that. So never go anywhere when you're doing a design without stating random assignment and without stating compare results. You've got to include it. Does the difference make a difference? Okay, it does sound kind of ridiculous, right? Does the difference make a difference? Well, what that means is how big of a difference do you need to see between two groups to state that, you know what, yep, those two treatments result in different outcomes. You might have some things that are similar, but where does it become important enough for us to actually comment on? Differences that are larger than we'd get from just the randomization alone are called statistically significant. Remember when we were doing a random sample and we were trying to figure out what happens, what should I expect to see just by natural random sampling variability? What happens when chance occurs? Or is this something that makes me kind of scratch my head and go, what? Now we're going to go later on into a lot of detail as to what it means to be statistically significant. At what point do we say, yeah, I don't think so anymore. There's something causing this. And there is kind of, I guess you could say, a line in the sand that we'll use. But for right now, we just want to look at the situation and make a decision. A statistically significant association, there's my cause and effect word. It's not cause and effect, it is slightly different. In data from a well-designed experiment does not imply causation. So again, statistically significant association does not always imply causation. And so what that means when we go through this, we're going to say something is associated with something else. We're going to very rarely say cause and effect. Yes, I did say before that an experiment allows us to test cause and effect. But the problem is that there are always going to be lurking variables when we're in the real world setting. And so in order to make sure that we're not guiding people the wrong way, we're going to say that things are associated, not that one thing causes the other. There's a strong association is what we'll typically say. And when we're talking about experiments and samples, both experiments and samples, remember an experiment and samples are not the same thing. We've talked about what both of these guys do. They both use randomization to get unbiased results. Remember, bias is just the stuff that we accidentally put in there that steers our results one way or the other. Sample surveys estimate population parameters. So that means that your sample needs to be representative of the population as possible. So if we're trying to measure AP statistics students, I'm not just going to ask all the girls. That's not all my population. I'm not just going to ask all the seniors. There are other students taking AP stats. Experiments try to assess the effect of treatments. And experimental units are not always drawn randomly from the population. We just can't always control that. So sample surveys estimate population parameters. Experiments assess effects of treatments.